Welcome to The Explainer, where we take complex source material and turn it into clear visual insights. I'm your host, and today we're cutting right through all those relentless buzzwords you hear every day to understand the actual foundational concepts of artificial intelligence. So whether you're a total novice or someone who works with tech literally every single day, we're going to strip away the hype and look at exactly how computer science defines and structures AI. To kick things off, let's just ask the big question. Bypassing all those sci-fi movie expectations, Terminators and all that, we really need to look at how computer science actually defines this incredibly broad field. And well, it turns out there isn't just one single definition. It's really more of a spectrum. Okay, here's our agenda for today. 1, the philosophy of AI, the what. 2, meet the AI agent, the how. And 3, navigating AI environments, the where. Section 1, the philosophy of AI, defining the what. So early on, thinkers focused super intensely on internal reasoning and human cognitive models. Back in 1985, John Haugeland defined it essentially as an effort to make computers think, building machines with minds, in the full and literal sense. This was a very cognitive science approach. The idea wasn't just to spit out an answer, but to actually trace the exact sequence of reasoning steps a human would use to solve that exact same task. But as the field matured, that focus started to shift. By contrast, look at Ray Kurzweil's later definition from 1990. He shifts the focus purely to measuring behavior and action, completely regardless of the internal reasoning process. For him, it's about the art of creating machines that perform intelligent functions. Basically, it really doesn't matter how it's thinking, just so long as the final action mimics human intelligence. And these evolving definitions, they create this foundational 2x2 matrix of AI philosophy. You can basically categorize systems by comparing those that focus on thinking versus acting against those that aim for human-like performance versus pure rationality. Rationality in this specific context is the ideal concept of intelligence. It just means doing the right thing. So you end up with systems trying to think like humans, act like humans, think rationally, or act rationally. A classic example of that act human-like quadrant is the famous Turing test. The setup is simple, but honestly, it's profound. Picture this. You have 3 rooms containing an interrogator, a person, and a computer. They communicate only via teletype, like a text chat, just to hide their physical appearances. The machine's entire goal is to fool the interrogator into believing it is the human. It is the ultimate measure of behavior over internal representation. If it succeeds, boom, we consider it intelligent in that specific behavioral sense. Section 2. Meet the AI agent, the how. Now, the absolutely crucial point here is understanding the concept of an agent. This right here is the foundational building block of modern AI. An agent is simply anything that perceives its environment through sensors and acts upon it through actuators. Think about it. Just as human agents use eyes as sensors and hands as actuators, a robotic agent might use cameras and motors. Even a software agent uses keystrokes or file contents as its sensory input, and then it acts by displaying information right on your screen. And this continuous logic loop, it's literally the heartbeat of an AI. The agent receives percepts, which is really just the fancy technical term for perceptual inputs, from the environment through its sensors. The oncoming information is processed and then sends actions back out to the environment via its actuators. This ongoing, nonstop loop defines the entirety of how an AI interacts with the world. So make this abstract idea completely concrete. Just think of a basic robotic vacuum in your house. Imagine an agent that only exists in 2 locations, square A and square B. Its sensors only perceive 2 things: which square it's currently in and whether there's dirt on the floor. Its actuators allow it to move left, move right, suck up dirt, or just do nothing. Its programming is brilliantly simple. If the current square is dirty, suck. Otherwise, move to the other square. It is a perfect, highly simplified demonstration of that agent environment loop in action. But you might be wondering, how do we define the rules for way more complex scenarios? Well, when we design task environments for these agents, we use what's called the PAAS framework. PAAS stands for Performance Measure, Environment, Actuators, and Sensors. Before you can even try to build a successful AI, you have to rigorously define these 4 exact components of its specific world. Let's actually apply this to a real-world example, something like a medical diagnosis system. Its environment includes the patient and the hospital. Its sensors are the keyboard entry of symptoms. Its actuators are the screen displaying questions and diagnoses. And most importantly, its performance measure, which is how we evaluate its ultimate success, is a healthy patient outcome while minimizing costs. Every AI system, literally no matter how complex, can be broken down into this exact PAS description.
Section 3. Navigating AI environments. The where.
First up, we look at observability. An environment is fully observable if the agent sensors can see the complete state of the board at all times. Think of a game of checkers. It makes the AI's job significantly easier because it never has to guess what's hidden from view. A partially observable environment, on the other hand, means critical data is missing. It's like playing poker, where your opponent's cards are hidden and you have to guess. Next is deterministic versus stochastic. Now, if the next state of the world is completely dictated by the current state and the exact action the agent takes, it's deterministic, very predictable. But if there are elements of unpredictability, say like a random roll of the dice completely outside the agent's control, we are dealing with a much trickier stochastic world.
Then we have episodic versus non-episodic or sequential environments. In episodic environments, the agent's experience is chopped up into isolated little chunks of perceiving and acting. It doesn't actually need to think ahead because each action is totally self-contained. In a sequential world, however, an action you take right now heavily dictates the states you will face later on. You absolutely have to plan for the long term.
We also have to consider time. The world is static if it patiently waits for the agent to think and process its next move. Take all the time you need. But if the environment can change while the agent is still sitting there deliberating, it becomes a dynamic challenge. Imagine trying to solve a crossword puzzle, which is static, versus trying to catch a fast-moving ball, which is highly dynamic. And finally, we contrast discrete environments against continuous ones. A discrete environment has a strict, limited set of distinct, clearly defined actions you can take. A continuous environment, however, has infinite or fluid possibilities. Like steering a car is continuous because there are infinite microscopic adjustments you can make to that steering wheel. So when we combine all these traits together, we instantly see the true massive complexity of AI. Take chess with a clock. It's fully observable, strategic, sequential, semi-static, and discrete. Because of that, it's relatively simple for a computer to master. Now look at taxi driving. It is partially observable, stochastic, sequential, dynamic, and continuous. It requires navigating infinite, unpredictable variables in real time. This perfectly illustrates why we've had chess-playing AI for decades, but fully autonomous driving is still a massive, ongoing challenge for us. To actually survive these highly complex, dynamic environments, a truly rational agent must be able to learn. It needs to utilize its percept sequence to achieve real autonomy. If an agent just blindly relies on the prior knowledge programmed by its designer, well, it lacks true autonomy. As our source notes, an ordinary clock runs perfectly on its own algorithm, but it has no inputs and learns absolutely nothing from experience. Therefore, it's not autonomous in the AI sense. So based on this definition of taking in percepts, processing environments, and genuinely learning from experience, I really want to leave you with a thought. As you look at the smart devices, the recommendation algorithms, and the digital assistants all around you today, ask yourself, are they truly autonomous agents navigating a complex environment, or are they really just highly sophisticated clocks wearing a digital disguise? Thank you for joining me on this explainer, and keep questioning the technology around you.